Okay, Catalonia. We will talk about something category theory related stuff.
Yeah, it's although I mean, as
Yeah.
you will see, I mean, you don't need to know category theory. Actually, I don't know category theory, but some of the concepts are inspired. From notions of category theory. So thanks for the invitation, and thanks everyone for coming. Actually, it's a big audience. I'm using the seminars back in Barcelona. I don't work in combinatorics. I do computer science, but in my work, I mean, computer science graph theory is important, as you know. So what? And it really, there are some concepts, some notions that are important in the work that I do. I mostly work in constraint satisfaction, but instead of giving a talk about constraint satisfaction, I just took some of this work that we did, which was originally motivated for constraint satisfaction, but I think it's interesting for a purely graph theoretical point of view. So I will not be talking about constraint satisfaction, only to motivate the work here. I mean, I don't know. I hope that I don't mess it up with the time, but probably I will not have too much time to do proofs or anything. It will be just explaining some definitions and some notions and some results that we got, but I will not get deep into the results. So actually that's the first main notion. As you see, I mean the title was scary, but all you are familiar. Probably I will not read this slide for this audience, but I'll just have it just to make sure that we're on the same page. So it is about graph homomorphism. And here, when I talk about graphs, they will be directed graphs because it makes more sense for in my setup. So I mean, I guess that you notice like a graph homomorphism basically is a from graph A to graph B is a map from the nodes of A to the nodes of B that preserves the edges of A. And I have an example, but I think perhaps I mean, tell me now. I mean, I understand that it's a bit. So now, I will generalize this because in my setting it will be very important to work in a more general setting, which is relational structures, for two reasons. One is because it's what you got when you work in CSP, and second because as we discovered, it also helps for the case of digraphs. So sometimes we will get some results for graphs using as intermediate relational structures. So it's not just generalizing for the sake of generalizing. It really gives us power. And actually, that's one of the messages of the talk. So let me introduce relational structures. I take a sort of logical perspective on them, which will be more convenient for what I do. So perhaps relational structures are less. I mean, perhaps less of you are familiar with relational structures. So here I will go slowly. So a relational structure, just you can think of as generalization of graph, in which now we might have not just one type of edges, we might have different types of edges. So think of it like colored edges, and so you know, this. Okay, so this will be the different types of edges. So you have n type of edges, and you can even generalize it more because they don't need to be edges. Each one of these relations, edges are just binary. I mean, collection of edges are just binary relations. They might have any arbitrariety. So we might have a collection of edges. That might be R1 might be just a R1 might be just a collection of edges. R2 might be a collection of triples, and so on and so forth. So that's relational structures. So now to be formal. So first we've set the signature. Signature is the type of relation that we have, and the associate and the arity of each one of them. And then once we fix a signature, a relational structure over this signature is basically has two parts, the nodes, which we usually is called domain or universe, but it's the set of nodes, and then the collection of relations. But now, instead of talking about relations, I'm using this terminology, I'm talking about atoms. So think of an atom as an edge. But that's an atom. An atom is an expression of this shape. So this is a collection of nodes, as many as the arity of the relation, and that's the symbol that says what type of age we're talking about.
Sorry, what do you mean by arity?
The arity, yeah, for every relation, we decide like the arity, how many elements we'll have.
Okay, I see. Yeah.
Ages will be, collection of ages will be a binary relation, relation of arity 2.
I see.
Triple. Thanks. Yeah, of course. I mean, it goes without saying that. Please interrupt me for the questions. So, for instance, digraph is precisely the structure of the signature has only one relation, E, which is binary, and then in my language, I mean, this is not my language. I mean, but actually, but I mean, in the language that I'm using, this will be the domain, and this will be the atoms. Of course, for digraphs, that's not super interesting because we always have E here, so that's why we don't use it. But in relational structures, it might make sense to have different symbols. And now, once we know what is a relational structure, we can generalize the relational homomorphism. It's what you will expect. A homomorphism from two relational structures of the same signature is a mapping from the domain of the first relation to the domain of the second relation that preserves the atoms. That means that if you have an atom in the first relation, the first structure, in the first structure, I will say structure because I mean, in logic you have structures which have also function symbols and everything, and here we don't have function symbols, we only have relational symbols. That's what this technically is a relational structure, but since we will only have relational structures, I will call it a structure to make it. So basically, you take every atom from the first structure, and the corresponding image has to be an atom on the other structure, and here the only thing that you have to pay attention is has to come to the same relation. So we are presenting this symbol. Okay, now I will be generalizing many of the notions for graphs generalize well to relational structures in a natural way. But with respect to cycles, there are a number of reasonable definitions of cycles in relational structures. Just so for concreteness, I will mention which one is the one that I will be using. But this is not important in a way. I will not get into details enough so that this definition will be relevant. It's just for concreteness. So I don't want you to get the idea that this is just one notion of cycle. I mean, this is the notion of cycle for me, but again, will not show up in the groups. So the idea here is that if you take, go back. If you have a relational structure, now basically what you do is from the relational structure you construct a graph, and then you define cycles and paths in this graph in the standard way. So actually what you do is not a graph, it's a multigraph. So you might have parallel edges. And it's my part that, so it's built in the following way. Let me see if I can see. Okay, I can go back. So the nodes are all the elements and all the atoms, and that's the big partition. And now you connect every atom with all the elements that belong to it, and adding as many parallel edges as necessary. So that's usually called the incident graph, although I'm sure that there should be some other names because these concepts are invented. So you do this, you get this graph, and now here you might talk about trees, you might talk about cycles, paths, and things like that.
So this graph loses information, right? Because, or would an atom RAB be the same as RABA?
Yeah, you're right. It loses the position in which it is, and there are some variants. They call it the factor graph, in which now this is labeled with the position and everything. But for ours, it's not necessary yet. Yeah. Okay. So now all this is about motivation. So I mean, if you believe that what I will say later is an important problem, you can ignore this because I will not use it. But I mean, that's a problem that is close to my heart. I work on it for long. That's the constraint satisfaction problem, which is basically the problem of deciding, given to relational structure, whether there is a homomorphism, whether there exists a homomorphism. And now here I'm introducing a variant of it. It's usually called the uniform satisfaction problem because we are fixing the second structure. So when you are given to a structure and you want to know whether there is a homomorphism, let's say we call the first structure source, the second target or template. So that the problem in its full generality is empty complete. So that's the end of the story. But then you can get like more complicated questions. If you fix the second structure, and now your input is only the first structure, now you have a bunch of computational problems, one for every way to fix the second structure, which is usually called the template. And then the idea here, I mean, this is very expressive, because if you fix your structure, then you can model some computational problems. I'll give you some examples. For instance, deciding if your graph is tricolorable corresponds precisely to CSP where the target is K3, because it's no, so you are given a graph and you want to know whether it's homomorphic to K3. That's the same thing as saying I'm asking whether the graph is tricolorable. To see why relational structures are interesting, so I'll encode a problem which, I mean, here I will encode also trisat, and here you'll see why relational structures really like, you need relational structures to encode it in a natural way. So that's CNF problem, satisfiability of the CNF. You've seen it, so you are given a propositional formula of this form, and you want to know whether it's satisfiable. Then you can encode this immediately as an homomorphism between two structures in the following way. You make A to be all the variables that appear in your formula. You make the domain of B to be 0, 1. So now you think of it, mappings from here to here correspond to us to assignments. And now we will build the atoms in such a way that only the satisfying assignments will be homomorphism. And to do that, you go clause by clause. So you take this clause here, and then you introduce in your signature one symbol. Here you have the variables that appear in the clause, and here you have all the valid combinations of assignments that for that clause. So now if you think on an homomorphism, we'll need to send X, Y in a way that is consistent with the assignment that satisfy the clause, and you'll do that for each another. So you see, I mean, it's expressive. It's a cool problem.
So here R, can you go back a little bit?
Sorry,
I was a bit confused. R, X, Y.
Yeah, the small buttons.
I'm putting.
Yeah. So how do you? So the first one is X or Y bar, right? So in the atoms we have R, X, Y. Does that mean?
Yes, I have atoms, not one atom for every literal, but for every variable. And then
encoded in the atoms, right? The fact that it's not Y is encoded in the.
Yeah. The fact is not Y is encoded here.
Oh, the right. You.
I just only.
So you want to make 0, 0, or 1, 0, or 1, 1.
Right.
Okay.
Okay, so now it's a good problem, and actually it was posed as an open question like many years ago to decide whether to decide whether for every template the problems can be solved in polynomial time or incomplete, because that was not even entirely clear at the time. Because I mean, these are a large family of problems. You take CSPs, and it was proved that if you generalize this set of problems in very mild ways, you get all problems in NP. So it's not even clear that we'll have sort of dichotomy, but the problem now is solved. I mean, that's Mysov result from 17 was proved independently by Zuk and Bulatov, and they proved that actually for every template it's either it's associated CSP is solved in polynomial time or is NP complete. And I will not present. I will not present the. It's not necessary. I mean, I'm just using this to motivate what we'll do. The only thing that I want to mention is that the hardness can be obtained by reducing from tricoloring, or actually SAT if you want, and using a very restricted type of reductions, which I will not define here. They are called gadget reductions, and here I'm using gadget reduction in a very specific sense. Gadget reduction. So it's kind of interesting that all the hard problems can be obtained by a reduction from a very simple reduction. from tree code. And this fact, as a consequence of this fact, you have a rich theory. It has a lot of algebra in it, but I will not talk about it. So that's a little bit the situation with CSP. Now, why I mention this? Because I mean, either if this problem is now solved, there are now some new problems, of course, because there were a lot of people working in CSP, and now they need to get a new problem. And one of the most studied ones. I mean, there is a lot of work in infinite CSPs, like where the domain is infinite, but this is one of the ones that receive a lot of attention. It's called the promise constraint satisfaction problem. And now here, the template is not one structure, it's two structures, B and C. And we know that B is homomorphic to C. Okay. And now the input is a structure of always of the same signature, and now we have some promise. That's what the promise is that is either homomorphic to B or not even homomorphic to C. So it's not this sort of thing. There's nothing in the middle. Basically, you need to distinguish between the two cases. I'll mention one particular example in a minute. So if the two are the same, then you get the standard CSP. But when they are different, this gives you more possibilities. So the best well-known example is approximate graph copy. So assume that here you have a click with P elements, a click with Q elements, and Q is larger than P. Now the input is a graph, and you have the promise that it's either homomorphic to here, so it can be colored with P colors, or it's not homomorphic to here. It can be colored with Q colors, and you want to know which one is the case. So this, I mean, there is a lot of big work going on in this problem. I'll fix P2B3 because I think this is the most interesting. I mean, the most studied case, and also I think where I illustrate what's going on very well. So of course, when this is K3, this is tricoloring. This has been known to be half ranges. Now it took quite a bit number of years to go to 4. So distinguish between graphs that are tricolorable from those that are not tricolorable. That was like a deep result. Now it took 20 more years to go to 5. That's a relatively recent result that uses this algebraic this algebraic approach that I'm not mentioning. Actually, these are two of my co-authors. And the other case is, for 6 is already on. So this is a little bit to give you a little bit of the flavor of the kind of results that you get in PCSP. PCSP now is like Wild West. Like very few things are known. There is a lot of opportunities here. Now, what we do know is that you can sort of generalize the same theory, and you get some results. Actually, you can prove things like this, but it is known so far. We know already that the theory is not powerful enough in the sense that you need stronger reductions, and this is what motivates a little bit. One of the, that's one of the important motivations about it. Okay. So now, end of motivation. I will get back to PCSP in a minute. So what are we talking? I will be talking. I need that will be the main concept here. So I'll use this terminology to refer to the set of all structures of some signature. And now, for me, I'm abusing a little bit the categorical terminology. A function is something different. It's just a mapping from the structures for some input signature to the structures of some output signature that preserves some homomorphism. So if you have an homomorphism here and you apply this mapping, you get an homomorphism. For those of you that know this, which I think you know better than me, this is not a function. I think what Jakub, one of my co-authors, knows told me is that this will be a functor in the thin category of the graphomorphism. So I mean, if this says something to you, I mean, I think I know what he means, but I mean, I don't want to go to this. I mean, but that's not all you need to know. Right? So that's a functor. That's something that represents this. Now take some function that goes in the opposite direction from the structure of the output signature to the structure of the input signature. And now we'll say that this pair of functors are adjoint if they satisfy this property for every A and every B. So you take every A and every B, and you want to know whether so A is in the input, A is in the input signature, B is in the output signature. You want to know whether the image of A is homomorphic to B. That's the same thing as saying that A is homomorphic to the image of B. And in this case, we say that L is the left adjoint of R, and the other one. But actually, we'll care more about right adjoint. I'll get. I mean, this is a basic issue. I'll see an example in a bit, but please stop me if something is not clear. So that's a very simple case for digraphs. So here, the first function basically computes the symmetric closure of the digraph, and the second R computes the maximal symmetric subgraph of the so let's see. So if this is G, G basically makes every edge symmetric. And the other one, R, takes this graph here and basically removes all the edges that are not symmetric. So if you have only edge in one direction, you just so now, I mean, it's very obvious that this defines an adjoint bar. So we have to see that we have an homomorphism from here to here, even only if we have an homomorphism from here to here. I mean, guys, I mean.
Can you go back to the definition? I
Yeah,
just
yeah.
wanna
Okay.
see the last line.
Yeah.
So LA. Oh, so A is S in structure and B is S out structure.
Yeah. In our case, it's graph, so S in as out is the same. But I'll mention it. I mean, I'll show it. So L takes the graph and makes the symmetric closure, and R takes the graph and forgets edges that are not symmetric. So I want to show that you
Should it be an R of H in the bottom then? Or? Should it be like an R of H?
Oh yeah. Sorry, my mistake. I'm so sorry. Yeah. This should be R of H. Yeah. So what I want to show is that for every G and for every H, I compute the image of G according to L, the image of H according to R. Now this is homomorphic, even only if this is homomorphic. And here is a strong case because actually it's even the same homomorphism. The definition will allow for different homomorphisms, yeah? but this is even the same homomorphism. So let's see, if we have an homomorphism from here to here, so you see the image of every, I mean, this is symmetric, so you are only using this, so certainly it should be matched on the top. And on the other hand, if you have that's the second direction is even easier. If you have homomorphism from here to here, the image of the homomorphism can only use symmetric edges. So if you remove the non-symmetric, it will also be an homomorphism. So certainly then it should be an homomorphism. So that's the concept. Any questions? Okay. So why do we care about this? And
I do have a question.
Yeah,
Yes.
thanks.
So we really just ask about the existence of homomorphism, or like should it be that like the same?
no, only the existence.
Only the existence.
Yeah. And to make it powerful, I think if it's only the same homomorphism, you will get very simple. I mean, to be honest, I didn't study it, but I presume that if you require to be the same, this would be like, will be like not super interesting. Will be like very few cases. Yeah, actually, I mean, these functors, they don't even change the domain. But a functor takes a structure and sends it to another different structure and might change the domain. That's we'll not explore this here, but yeah. So then it will not even make sense to talk about the same morphism. Thank you. So now, why do we care? And we care because this gives us PCSP reductions. And so assume that we have an adjoint pair, and now in addition we want L to be computable in polynomial time. Then L defines a reduction for every B and for every C, defines a reduction from these two problems. I'll show it in a second. I mean, actually, it's just follows from the definition. It's nothing deep. So let's take an instance here. If it's a positive instance here, so it maps to B, then because it's a functor, the image according to L should map to LB. Nothing going on here. And now, when to need to show that negative instances are mapped to negative instance, I do the contrapositive as usual. So take any instance such that the image is mapped to C. Then I'm using the adjoint condition, and I get this maps to this. And yeah, if you do the contrapositive, that's it. So if A is not mapped to this, then image. And as you see, I'm only using one of the conditions, one of the implications in the definition of the adjoint, the definition of adjoint. The other one is to make sure that this reduction is as powerful as possible. I mean, this needs to be a bit formalized. I mean, I don't even have how to formalize this, but that's the idea. Okay, and actually this is not like some potential possibility. This has been used, and actually it was Rodna and Sidney the first that realized this, and they used one that is very well known in graph theory. They call it the R-digraph construction, which I think if I have the time I'm going to use. Then choosing it with some extra work, they prove some result. I will not get into details, but there was, I mean, this is the state of the art for some values of K. So it's really powerful, and you really cannot do these reductions using the actual technology that we have. So this is an example that shows that you need better technology for reductions. And with okay, if this works here, let's now study adjunctions in full generality. Let's see what is in graph theory, what results we can use, and then see who can we apply it to PCSP. Okay. So now, okay. So what is known? So first thing is like what is known. And now we observe that, I mean, this has been studied, and in particular there are a particular type of functors which are called Pultr functors, which they were defined in the 70s. There's not a lot of literature about it, but it really comes very handy. Let me introduce it to you. Now it's all about the homomorphisms. So that's the following. So I'll talk about the graphs. Yes? Okay. Sorry, I missed that. So you fix a graph G, and two nodes from this graph, A1 and A2. And then for every choice of G and these distinguished nodes, you define a functor. And the functor goes in this way. The image of any graph H is the new graph that has the same node set than H. So if H is this, we'll have the same node, so that we don't change the nodes, we don't change the H's. And now the H's here corresponds to the all the pairs in H that satisfy this condition. Let me explain this. This is the standard homomorphism, but now I'm requiring that this maps to this and this maps to this. So another way to put it is, you take all possible homomorphisms from this graph to H, and for every such homomorphism H, you add as an H the tuple HU1, HU2, the image of A1. So if you think in this particular case, that will be the image of the U1 and U2 will be all the nodes that are separated, that are joined by a walk operator. Make sense? Okay. So yeah, that's the kind of thing that you can do. So let me mention that this is a fragment of power functors because it doesn't change the domain. You can also change the domain. This is a more complicated definition. We can do actually with Mark. We work with this. There are some new results about this, but I will not talk about them because just I don't want to do a lot of definitions. Okay. So then what's on in the literature? So this was studied by Foniok and Tardif, and they proved that every such function has a right adjoint if it's a tree. And I mean now with Mark, we have to we don't understand this super well, but I'm just I was not prepared to give a talk on this. But that's some result that was known. Now, so what we want to do, but that's not a lot. I mean that's not a lot. I mean, for our purposes, we need to understand it better. So we want to generalize this in a number of dimensions. The first one is we like to consider functors that are defined not by one graph, but by actually by a family of graphs. So let me see the idea. So before, I mean, in a standard power functor, we'll just have one graph. But now we want to allow possibility to have two graphs with two distinguished nodes. And now, using two graphs, then we can construct the union of the edges that will produce each one of them separately. So basically, we want to be able to do unions, and that's contemplated by just considering sets of graphs with two distinguished nodes. So, for instance, if we use this, then we'll say, I mean, now we can construct the function that takes a graph and produces the set of all the pair of nodes. I mean, the edges on the new graph are all the pair of nodes that are connected by a walk of length 2 or a walk of length 2. But we also want to deal with the case in which is even infinite. We'll see how this can be done. And finally, we want to do it for relational structures. And as I mentioned before, not just because relational structures are important for CSP, it's just that even if you care about graphs, you can get a lot of results. And actually, that's the only thing, the only interesting, the only idea here is that you do very simple constructions of relational structures, and you can do a lot of things over graphs when you compose them. And I think that allows us to go much farther than them, doing things that are very simple because I cannot do complicated things. I can do this. So that's the idea. Okay. So how does it go for relational structures? Let me show you the definition. Now you have some input signature and some output signature. I'm spelling out only the output signature. I would not need to know the input signature. And now you can imagine how it goes. Before, to define the edges, we needed a structure with two distinguished elements. Now we want to define M relations, we will need M structures. And the number of distinguished elements in each structure will correspond to the arity of the relation. Right? If you have two distinguished elements and then you look at the image, you get a table of elements and so on and so forth. So that's the setup. So in this way you can generalize these power functions for relational structures. So same thing. I mean, you can pass the definition, but that's what you just did. And I mean, I'm going a little bit fast here because I will use a different language in a minute. So it's not even that important. But in a way that's not complicated. And we managed to generalize this. In the previous result, now we can show that L has a right join if and only if we have a tree for every. So that's a generalization of the Tardif, Foniok and Tardif result.
Do you say if and only? Do you say if and only? Or did you say if and only?
No, that's perhaps I said. Did I say if and only if? No, I didn't want to say it. So sorry, probably said no. It's on if. although there is an if and only if, but not this one. You have to summarize it a little bit, but yeah, I cannot. I mean, yeah. Now, but what I'll do, I mean, this is one paper, but I won't talk about this paper because actually there is a much better language to work about this that goes via logic.
What is it? What is a tree in this context?
Yeah, a tree is you look at the incident graph as I mentioned before, and it doesn't have cycle. Yeah.
Okay.
So is there an example which has a cycle that has a right? I mean, has a right origin?
You can have it because your graph might be homomorphically equivalent to something that. So in a sense, the idea is it's almost only trees. But you can have things that are not trees because they are homomorphically equivalent to a tree. And then if it's homomorphically equivalent to a tree, I mean, you get the same function.
Like bipartite? Or?
Bipartite will be an example, but yeah. I mean, you take something such that its core is a tree. Although here in the core we have to preserve the distinguished elements, so it's not like a full. If it's core, it's a tree. Yeah, but that's not the converse. I mean, when you try to do the converse, you have to use unions. So well, I mean, I don't want to say that, but now that we are almost there. So R has an right-joint, even only if GI is equivalent to the union of trees. That is equivalent to the union of trees. That will be like the if and only if condition. Okay, so now, but again, I'll use a different language, which is okay. So our idea here was that to define functors in a logical way, and once you have the right language, then proofs become very simple, and I think so. In a way, actually, our previous law was already, I mean, in the pipeline was already proved, but it would have been more honest to withdraw it because now we can prove things in a much simpler way and not inflict the complicated proof that we had in the previous paper because this language is much better. So but I mean, it requires a little bit of more definitions. So I will use sigma to denote a collection of logical sentences that, I mean, you have some signature and you write expressions of this form. You have a conjunction of them. There is some technical assumption which comes because I mean this comes from historical reasons, not really essential. You can ignore it. Actually, everything works even without this technical assumption. But if I want to be faithful to what is in the paper, we didn't do this assumption. So for instance, this will be a particular example, only one sentence. So you have digraphs, and you can express things like this. So basically, you can express that the graph is transit, right? And so
maybe there's typo.
Yeah.
X Y
Y,
Y
Z.
Z.
Oh yes. Sorry, my apologies. Yeah, this is right. Thank you. Yeah. But, and now, I mean, the regions they call it I think universal. I mean, universal Horn theory. But in any case, there are sentences of this one. Now, these sentences are very nice because you can define in a very natural way what is the sigma closure of a structure. The sigma closure of a structure will be the smallest structure that contains the original structure and satisfies all these sentences. And you see that this is defined in a natural way because it can be obtained as a sort of fixed point. I mean, I can take this as an example. So assume that you're given a graph. So take any assignment of the variables that satisfies the antecedent of the clause of the implication. If the consequent is not there, you add it, and you iterate. You get a fixed point, and this will be the sigma closure. And you can do it for this, but you can do it for every time that you have this. And the sigma closure is a function. So if you start with particularly, I mean, if you start with two graphs and that are homomorphic, you make the transitive closure and they will be homomorphic. So that's the idea, but sigma closure is still limited because, among other things, you are forced to use the same signature, want to be more free. So what we do is basically we allow ourselves to change the input and the output signature in sort of the most in a very natural way. So what we'll do is additionally, so S is the signature of we use in all expressions, and now I select some of the symbols and I put them in the input signature. So I define the input signature to have only these symbols, and I select some of the symbols, I put it in the output signature. And now this, so now I construct my function, which depends on this sigma, this set of sentences, the input signature and the output signature, and it goes as you expect. So the input is a structure over the input signature. The input signature is a subset of S, right? So you can see this structure as a structure over signature S. Now you make the closure, and after doing the closure, you forget everything that is not in the output signature. And by doing this, you get more expressivity. That's basically you're doing the closure, but you're allowed to work a little bit with the input and the output signature. I'll get an example in a second. And doing this, I mean, these define functors, and so let me see. One went a bit shallow. Yeah. But so for instance, you can compute the transitive closure, we saw that before. Interesting thing is here is that you can deal with the case. I mean, if you try to translate this in terms of Pultr functors, you can see this as a Pultr functor in which you have an infinite set of graphs. I mean, now take a graph and it belongs to the epsilon closure, if and only if it has like two elements are connected, if and only if they have a cycle. They're connected by a block of length 2 or 3 or more. So basically, if you want to express it, it will be in this way. So you can deal about infinite graphs in a natural way. But now let's see an example in full generality. So this will be something like this. So that's your signature. It has three symbols, three types of edges. All of them are binary. So you have these three types of edges. Okay, I need to go back. Sorry, I didn't mention something. So let me introduce some terminology, some notation. I'll do this. I mean, since the universal quantification is always implicit, and implication as well, so I'll just write any one of these sentences in this form. I know that here it will be much better to use an implication. But for historical reasons, this comes from database theory, and they use this terminology, so I'm using this. But every time that you see this, think of an implication. Basically, it's an implication. I mean, since everything is quantified universally, I can move it, and here I have conjunctions, but I just write it in this way. Okay, so
Could you?
Yeah, of course.
Could I see one? Just one slide. Okay.
For what?
No, it's okay.
Okay.
I just want to.
Okay.
Show.
So I'll call this the head. The head will be the consequent, and the body will be the answer. Okay. Now this is an example of full generality. So again, all these are implications and so on. So what's going on here? So this is my input. Input is E. So I have three types of H's. One of them are called E, the other are called even, and the other are called odd. I'll use colors. So E will be black, even green and not red. And this is my sigma. So now I get as input a structure over the input signature. So you can think as a graph. So I only have black edges. And now I make the transitive closure of this. So you can think of this as rules that allow me to add new edges. So for instance, If I have this, it says every time that I have an edge, I have also another edge. So doing this. Then I have this, I say, okay, if I have another edge and I have a standard edge, then I have an even edge. So yes, and it keeps iterating until I reach sort of a fixed point. So you see, this is sort of defining, I mean, by the way that this is sort of, it can be seen as a recursive definition of these two predicates. Basically, this what holds if there is if x and y are adjoined by a walk of odd length, and even if they are joined by a walk of even edge.
So does it create a loop as well, like even xx?
Yeah, might create. Yeah. Depends. Yeah, but perhaps I mean, perhaps the example is not correct. And then finally, you just forget everything that is not in the output signature. So you see, this is a function that takes a graph and basically now produces a new graph where two nodes are connected if they were connected by a walk of even length. Okay, so that's what's okay, so now what can we do with this? Well, as we will see, we can do all Pultr functions, and that's take now. I mean, forget about the head of the rule and think of the bodies, and you think of the body of the rule, and basically there is a one-to-one correspondence between the bodies of the rule and the digraphs. Basically, like this corresponds to the atoms. I mean, I'm ignoring isolated nodes because with respect to homomorphisms, they don't care. But I mean, there is one correspond. I mean, this you can see this is a collection of atoms. Basically, correspond to the collection of atoms of person. So there is a one-to-one correspondence between one or the other, and it's not difficult to see that if you have some other graph H, the assignments that satisfy the body of the rule correspond precisely to the homomorphism of this graph. Basically, it's the same thing, different language, but the same thing. So by doing this means that I can get all functors. Imagine that we have the Pultr function which is defined by G with distinguished nodes U1 and U2. In this case, I will just do the rule that produces this new predicate, and these are my two variables here. So basically, our functors correspond. You see the special fragment in which we have only one rule, which is also actually like of this very particular shape, but we can do way more things. Okay, I'm gonna rush a little bit because I'm slow. I'm terrible with preparation time. but basically, what I will do because I get it. What we can prove is that if you have just final definition. I will call this thing like this sigma plus the input and output signature. I will call it a Datalog program. That's not what is strictly speaking a Datalog program. I'm abusing a little bit the terminology. The Datalog program has a number of technical definitions that are there. Sorry, technical restrictions that are there for historical reasons, but they are not important. So you can ignore them. I just want to, make sure. I want to say that this is not exactly a Datalog program, but actually it's even better. In a way, by preparing the talk, I discovered which is the right setting. It's better than that. So what I would like to do is to understand which restrictions on the Datalog program guarantee that the associated function has a right adjoint. Yes, so I have a Datalog program, and which conditions do I have here, and then from this be able to rederive all the previous result and get some others. So now it will be painful. I will be giving a number of definitions of some fragments of Datalog program that some conditions that need to be satisfied, but it is fast. So, first one, a Datalog program is acyclic. So basically, you look at the body of the rules. Again, a body of the rule can be seen as a graph or as a structure, because it's a collection of atoms of a structure. And then basically, you say that this is acyclic if this is acyclic. If this is satisfied for all possible rules, then the Datalog program is acyclic. You can talk about connected, same way. You can talk about recursive. Now, recursive means that you have the same predicate that appears here and appears here. So the same predicate appears in the body and in the head. I will, you know, but since this is only relevant for some part of the talk that I will not be able to get into it, so perhaps I mean I want to leave some time for questions. So I might escape this. Now, monadic. Monadic is that every predicate that appears here has a relative one. And now, finally, this like more technical one, almost monadic. Is a generalization of monadic that allows us to push our results a little bit more. So what means almost monadic? So a Datalog program is almost monadic if you can obtain it from a monadic program by doing the following operations. So you start with a monadic program, but now you want not to be monadic, you want to be more general. So now first you decide all these predicates that are monadic, which arity you want them to be. So you might decide them to be binary, ternary, whatever. So in this case, for instance, we decided this to be binary and this to be ternary, and I expand them, and now I have to fill the rest of the positions. So how do I fill them? I have one strong restriction here. Basically, I cannot repeat any variable that has been used before in the same way. So we'll use something like this. And here, then I can do everything I want. So here I can do everything. So that's almost, I mean, it's slightly more powerful than monadic, but allows you to do cute things. For instance, you can do the transitive closure, right? For instance, imagine you start with this monadic program. This is monadic certainly. Now you make R binary, and now here you only can use a different variable. I will use Z, and now here I can fill it in the way that I want. So I will use Z. So you can see I can do transitive closure. It seems very, very similar to monadic, but it gives us quite a bit of power. While we can extend, we can do so that's all the restrictions. Now, finally, to the result. Okay, so basically, show that every Datalog program that satisfies these properties has a right-adjoint. And which are the properties? Has to be connected. This is what I said before. Has to be acyclic. And has to be almost monadic. So you need to satisfy the three of them simultaneously, and then you get a right-adjoint. And this gives you like of course we will prove all the results, and our proof is super simple. I mean I don't have time to do it, but you know this happens when you work in logic. This kind of proves that if you know what you are doing, they are trivial. I mean, you just have to know what you are doing. I mean, there is no magic or anything. I mean, there is nothing going on. I mean, it really super simple. Okay, I mean, I over-prepared material, but I mean, I don't want to inflict them on you. So I will leave it here, and I'll leave some minutes for questions.
Thank you. Any questions?
Okay, okay, I have a question related to the Pultr's Pultr. I'm not precise with the pronunciation. Okay, Pultr.
So the first definition, when I introduce it. Okay. Wait to go back. Wait.
I think that's fine. I also think that in the general relational structure, thinking about the Diamond graph is also a kind of functor. Maybe just take.
Okay, you take a rational structure and
Yeah, I
and you,
think Diamond. So if two relational structure have yes, a map between them, I think there will be a natural map between its Diamond graph.
I will see if it makes sense. Anything with
Because if two elements are related and some in here and it might
Yeah,
also in here.
yeah,
So,
yeah.
if we extend the notion of that function into a general relational structure, I'm just curious about, are there any other approach about thinking
Okay.
the function between its Diamond graph?
Okay, I see. If you look at the Gaiman graph, you're losing part of the information.
Yeah,
So it's a weaker notion. So I guess that in some context it would make sense, but I mean if you have a ternary tuple, you in your definition now you require that the mapping preserves every pair of them. So
I see.
every pair. So you have a tuple. Now you yeah. So 182. According to the definition, you require that there is some tuple such that, and for every pair of them, but it's a bit weaker. Of course, there may be some context in which this might be the notion that you need, but it's a different notion.
Nice.
In order to construct a reduction, then we also need the condition that LP can be computed with polynomial. Is it trivial, or there is also some non-trivial?
Well, I put it in the assumption. So you need a pair, an adjoint pair, and you want L to be computable in polynomial time. In these particular cases, in all those that we are considering, they are computed in polynomial time. I mean, if you look at that example that I showed with all the colors and everything, basically is this kind of iterative process. At every iteration, you are adding a new edge, so the number of iterations that we'll do will be at most the number of possible edges. So if you, I mean, you need some sort of bound on the additive, but you get this for free once you bound the signature. So yes, all this, but yeah.
It should be run in n to the some largest ki.
Yeah.
To the plus some constant.
Thank you. Yeah.
In your main theorem, how tight is it? So if you remove like any condition, then there are examples where it fails?
Yeah. You need the three of them. Of course, that doesn't mean that I mean there may be some better ways to combine them, but yeah. You need and in some cases this is very tight. But I mean, for instance, in the case of non-recursive Datalog programs, they have to be three. I mean, modulo homomorphic equivalence, but it's still we don't know. It will be a very nice, you know. I didn't have the opportunity to say, but I mean, this looks like, I mean, we really reach at this definition to see, okay, we have this idea for a proof. Let's see which conditions we need to the proof to work, and it looks a little bit ad hoc. But then we discovered that actually this corresponds to some fragment which is very robust. I didn't have time to do this, but we saw that this corresponds to the functors that can be expressed by some fragment of logic, monadic second order, which for us was modulo some technical assumption, which was for us a surprise because again it was very ad hoc. Okay, so what do we need for the proof to work? And then I think we hit something, and one of my co-authors says that there are some connections in some other places because I think it's a natural fragment in a way, but yeah.
So just kind of the slightly bigger picture, this would be to show hardness for some PCSPs, assuming hardness of other PCSPs.
Right. Yeah, so it's a long project. The project is understanding well this, and then once you have your notion of reduction, then you have to see what's going on the other side. This I didn't say, but so the idea is. So you have PCSP, say AB, PCSP, CD, and you want to see whether there is a reduction, and you fix what type of reductions you are using. If you are using this type of reductions, which is called gadget reductions, so let me call it. It can be shown that you have a reduction from this to this, if and only if there is some algebraic property preserved between the templates. I don't want to, but there is some high dimensional symmetries here, the polymorphism there. So and then there is a minimum morphism from these symmetries, from these entities from here to here. So that's another part which I didn't mention. So there's a connection within these reductions and what's going on the templates. This is well understood for gadget reductions. Now we want to have a well-behaved, more general notion of reduction, and then see what's going on in this part. We did already a little bit of it. We do that for when this is gadget, because we understand reduction that also has to combine well with the gadgets. We took monadic Datalog with gadgets, and it behaves well, and it has some algebraic correspondence here. And I mean, we understand what is the algebra correspondence, but still we don't understand it well enough to be able to use it. but that will be the overall picture.
Is it the Datalog program that kind of does the reduction? Or?
Yeah.
Okay.
So the idea is to do this plus some Datalog program. Yeah, because in a way, I mean, if you're familiar with this, Datalog program is consistency. So in a way, you're doing consistency. So you want to use consistency not only to solve the problem, but actually to do reductions.
Right. Any other questions? If not, let's thank the speaker.